Hello, we'll be looking at the solutions for dual nature of matter and radiation questions asked in the JEE Test 5. A couple of questions require shortcuts, other questions requires concepts, especially those involved with force acting on a surface due to light. So we'll gather ourselves up and make use of as many conceptual shortcuts and approaches as possible. Right, we'll begin. The very first question is relation between maximum kinetic energy and stopping potential. They have given stopping potential. How do you find maximum kinetic energy? Well, we know kinetic energy maximum has to do with simply EVS, right? So in all these options, whichever gives you 2 times 1.6 into 10 power minus 19. 1.6 into 2 is 3.2. The only option which says 3.2 is option C, hence option C should be correct. One relation, kinetic energy is EBS. Then, well, the second question is what requires a shortcut. For an electron, the de Broglie wavelength shall always be 12.27 by root V angstroms, whereas for a proton, it shall always be 0.286 by root V angstroms. It will help you immensely with protons and electrons especially. And remember, we will always put the de Broglie wavelength in angstroms, but given here is in meters. So when I convert this meters to angstroms, I will get 10 to the power minus 10, into 10 to the power minus 3, which would give me around 10 to the power minus 3 angstroms. Okay, then it is straightforward math. What you do is you make use of this relation. Root V is 0.286 by 10 power minus 3. This 10 power minus 3 will go to the numerator. It will become 286. Okay, 286. Root of V should be equal to 286. Let's just have a look at the four options. Which one of these four would likely give square root as 286? Okay, so V would be 286 ka whole square. Don't waste time in calculating 286 ka whole square. We'll just approximate. 286 is just lesser than 300. 300 square would end with 9. So 286 should be closer to 8, right? So I can eliminate A and I can eliminate D. Between B and C, which one is most likely to be right? So I can express this as a 2.86 into 10 to the power 2 the whole square. It would lead me to 2.86 the whole square into 10 to the power 4. I got it. 10 to the power 4 should be the exponents. That should be option B. 286 ka whole square. 286 can be written as 2.86 into 10 square. When you square it, you get 2.86 ka whole square into 10 power 4. 2.86 ka whole square is nearly 8 or above 8, definitely less than 9. So 10 power 4 is what gives me the right answer. Second one goes with B. Now, question number 3. Surface is irradiated with some radiation, UV, they have told. Wavelength is zero point 0.2 micrometers. What is the maximum velocity of electron? That is also is given. Find the work function of the surface. The work function for the surface is phi equal to hc by lambda minus half mv square. Lot of stuff to uh, do with this. Reason V is given in terms of a meter per second. First, I have to put it over here, right? I have to put it in that equation, the V value, convert it to EVs. I can convert this to EVs very easily. Reason I know that the energy in EVs is always equal to 12,400 by lambda in angstroms. I can convert micrometer to angstroms very easily, so that's not a question. That's not a task. The ask is half mv square. V is given in meter per second. How do I convert it to EVs? And then I uh, take it up? How do I do that? That is the time consuming part of this. There's no shortcut per se to do this. So that this would actually consume some time, but all the concept involved is threshold function is supplied energy minus maximum kinetic energy. That's it. Well, that is about question number 3. Now, question number 4. Energy flux is given. Number of photons incident on Earth per second is what being asked. This can be addressed with one formula. The formula is P power equal to intensity times area, and power is also equal to NhC by lambda. Two golden formulas. Power in the photon picture is given as intensity into area. Power is also given as N. N is number of photons emitted per second into Hc by lambda. What quantity is this? This is power per unit area. So what they have given in this box is intensity. And in the question, they're asking number of photons incident per square meter. So I can take area to be 1 meter square. Intensity is given, area is given. I can find out power. Power is nothing but whatever they have given in the box, that itself. Now, I will use this info over here, NhC by lambda. Well, in this, Hc by lambda, H is Planck's constant, C is speed of light, and lambda value is given as 550 nms. I have to convert everything to SI because look at the units. It is every option has SI unit. So convert lambda to SI and then find out the value of N, where N is number of photons emitted per second. Again, this is calculation intensive. Only if you're confident with multiplications, divisions, approximations, then you can do this. Otherwise, advise that you skip this for the first attempt. Now, question number 5. In question 5, very cleverly, I will choose answer as all of these. Reason, this is a photo conducting sheet and source is always going to be, you know, maximum intensity is going to be here and it always spreads out. Light always spreads out from the source like this. So as I move from this position to this position, intensity of the light goes on decreasing. This is the brightest spot. As I move up or down, intensity sorts of keeps decreasing. Okay, because the distance from the source is increasing. You can see intensity is always proportional to 1 by d square. So as I move up, the distance from the source is increasing, so intensity is reducing. If intensity is reducing, what can happen to photoelectrons? We know that photocurrent is directly dependent on intensity. If intensity is reducing, photocurrent would reduce. Therefore, option A is right. What about option B? Option B tells, well, the electrons which are being emitted will leave behind a positive charge. Right? So after some time, what will happen is there will be some positive charges over here, and light is coming, and it is incident on the sheet. It will be very difficult for the electron to escape as time passes by, because electron will feel some forces of attraction towards this charged sheet. So as time passes by, electron emission would become more and more difficult, or electron would be emitted slowly because it has to spend some of its energy in overcoming the electrostatic force of attraction. Therefore, maximum kinetic energy of electron decreases. If two statements are right, I don't even read the third statement. I will simply mark all of these because there's no option which says only A and B is right. If A and B is correct, definitely C has to be right. And hence, for the fifth one, the right option is all of these. Now, coming on to sixth one. Sixth one, the biggest hint is all the three sources have equal intensities. Equal intensities means equal saturation current. Which of the graphs shows equal saturation current? This shows equal saturation current for all the three sources, and hence B is right. I don't bother about finding their stopping potential. Stopping potential can be found out by EVS is equal to HC by lambda minus phi. We need to use 12,400 by lambda in angstroms for this to get the answer, right? If you notice, it makes sense. All both P, Q, and R, they might have the same stopping potential. Reason, the threshold functions of PQR are different, and the lights which is shining on them, that is also different. So this combination, the difference might turn out to be the same if you do the math. So the most appropriate option is sixth one, B. Now seventh one. Seventh one is force exerted on a surface if the surface is absorbing 40% of light and reflecting the rest. Well, force acting on a perfectly absorbing surface is given by P by C. Force acting on a perfectly reflecting surface is 2P by C, where P is power in the incident light. But the problem here is the surface is neither perfectly absorbing nor perfectly reflecting. So what can I say? I can say that due to perfect absorption, how much force it is experiencing, only 40% of a power is getting perfectly absorbed. So for this, I can write 0.4 P by C. Okay. And what about the perfectly reflecting component? Perfectly reflecting component would be, if it is absorbing 40, it is reflecting 60. So it is 0.6 P it is reflecting and multiplied by 2 by C. So this would be individual forces. This one, whatever you're seeing, it is due to the perfectly absorbing component. And whatever you're seeing over here, it is due to perfectly reflecting component. And the total force would be sum total of these two. The light reflects some of these. Reflection force would be this. It is absorbing some power. So due to that, it would be this. Add both of them, you'll get the answer. That would be seventh question. Power is given as 60. C is speed of light. That anyway, we know. Now going on to eighth question. In the eighth question, let us examine all the options. The first one says frequency is equal to frequency B and intensity of A is not equal to intensity of B. If frequencies are same, right, then the maximum kinetic energy is same. If maximum kinetic energy is same, then stopping potential is also same. We remember this. Stopping potential is always dependent on frequency, whereas saturation current is dependent on intensity, right? Now, saturation current is different for A and B. So intensities will not be the same, but since the stopping potential is same, I can say that uh, both frequencies should be same. Only if frequencies are same, then the stopping potentials would be same. Because stopping potential is determined by only frequency. If stopping potential is same, frequency should be same. Therefore, option A is perfect. Since this is not multiple correct type, if I hit gold in the first option, I won't even bother to go to B, C, and D and check. The first option itself is correct. Now, nu A equal to nu B and IA is not equal to IB. Since their saturation currents are different, the intensities are not same. Right? What can I say about B and C? Well, for B and C, I can say the saturation current is same. Therefore, IB equal to IC, but their stopping potentials are different. So therefore, nu B is not equal to nu C. Okay. No such option exists. It is just for our understanding. So that is for question number 8. Question number 9. Stopping potentials corresponding to wavelength so and so are so and so. What is the work function of the metal? They have just given uh, stopping potentials. Okay, stopping potentials for 4000 is 1.3. For 4500, it is 0.9. They're asking for 5. Okay, and uh, and there is the voltage units here are expressed in, you know, uh, V, volt. So how do we go ahead with this? We make use of Einstein's photoelectric equation, Hc by lambda equal to phi plus EVS, where EVS is the maximum kinetic energy, right? In terms of stopping potential. Hc by lambda, I won't use it as it is. I will use it in the 12,400 by lambda in angstroms. So everything is in angstroms. So for example, if I put 12,400 by 4,000 is equal to 5 plus EVS. E for that, I mean V for that is 1.3. So 1.3 E. Similarly, I can put 12,400 by lambda. Lambda is 4,500 angstroms. That is equal to 5 plus EV, and that would be around zero point 0.9 E. We need to be very clear with this. You should not be putting E over here. Reason, I am expressing everything in the unit of electron volt, including threshold function. See, threshold function is also in EVs. So you should commonly made this, you will write E over here. You should not be writing E. Since I've already expressed EV, everything in terms of EV only. So it is simply 1.3 and zero point 0.9. And with this, we need to find the we need to find the work function. Okay, there are two equations. You can make use of that, but there's only one variable. Do we get two work functions? No, we don't get two work functions. So that is about it. So whichever is, uh, the least, you can go for that. That is question number 9. Now question number 10. With respect to the photoelectric experiment, match the following question is given. We'll try to play smart. I'll just try to get correct answers for one. I'll get correct answers for A now. Frequency is increasing. Intensity is constant. What depends on frequency? Frequency determines stopping potential as well as the maximum kinetic energy, isn't it? So stopping potential will increase and maximum kinetic energy also increases if I increase the frequency. So A option should go with P and R. So which of the options says A goes with P and R? Only C and A. I can eliminate B, I can eliminate D totally. Now, let's go with B option. B says for the first option, B goes with Q and S. Here also B goes with Q and S. Here goes D goes with P and R. Here also D goes with P and R. The only differentiating factor between A and C is this. What would happen if anode and cathode separation distance is increased? Well, actually, if there's nothing which is dependent on the distance between anode and cathode, okay, especially if I talk about stopping potential, let us say what is this talking about? Well, if the distance between anode and cathode it is increasing, what is happening to the saturation photocurrent? It will remain same because saturation photocurrent depends only on the intensity of the incident radiation. It is independent of anode cathode distance. So I can eliminate option C. Correct answer should be option A. So while explaining, it will take a lot of time, but while thinking, it will take very less time if you go by this logic. Get correct answer for any one of these and eliminate most of the options. That would be question number 10. We'll go forth. We'll go forth for the numerical type, question number 21. Question number 21 has stopping distance concept. The nucleus charge is 120 E. The closest distance given is 10 femtometer. And they're asking what is the de Broglie wavelength of the proton at its start. Here, it will have some kinetic energy. So I need to find the de Broglie wavelength. Well, what is the logic for stopping distance? Well, I can take this. initial kinetic energy of the proton, half mv square, okay, has been consumed completely in this scenario, right? Its initial kinetic energy has been completely converted to the potential energy of this combination, which is K Q1 Q2 by R, which is 10 femtometer. Femtometer they have given is 10 power minus 15. And E value we know already, K Q1 Q2 by R, that is potential energy, right? Okay. So what is the logic? The logic is I don't need to calculate anything much over here. It is just this. I'll tell you why. Once you calculate this, you will get the initial kinetic energy of the proton. Once you get kinetic energy, how will you find out the de Broglie wavelength? The link now becomes obvious. Lambda is equal to, for the uh, proton, it is lambda equal to h by square root of 2m E or 2m kinetic energy. 2m times kinetic energy. Straight up. Lambda is equal to h by square root of 2m kinetic energy. Kinetic energy I have already figured out from this expression. I put it as it is, and mass of the proton they have already given for you, and h value, h by E actually. H by E has been given. You will see why. They have given h by E because a kinetic energy has E squared, 120 E into E. When you take E squared out, it will become E. Then h by E value is given over here, 4.2 10 power minus 50. So make use of these values, get the answer. It is numerical manipulation. The concept was you can find initial kinetic energy with the help of stopping distance, energy conservation, and then link kinetic energy to the Broglie wavelength. Question number 22, by far, is the most conceptual question you can ever encounter in the dual nature. I'll tell you why. Uh, as the sphere gets positively charged, okay, the escaping electron, as I explained in the earlier part of the video, it becomes more and more difficult for to escape. So now when light is falling on it, its energy hc by lambda is not only consumed in overcoming the threshold function, it is not only overcome in giving it some kinetic energy, it is also used it's also used to overcome the potential energy of electron with this charged sphere. That's the ultra concept. Why wasn't it happening in this setup where there was, I was emitting this in the photoelectric effect when I was using this? Why didn't I use potential energy thing here? Because the potential energy was, it was that term was taken care of the battery. It was maintaining a constant potential difference between here, but between the cells, right? So whatever light was incident on this plate, it used its energy only to overcome the threshold function and only to give it some kinetic energy. The potential part was taken care of the battery always. So it wasn't, it was given externally. But here, light itself has to perform the role of a battery. So what is the potential energy term? Potential energy term would always be K. Charge on electron is E, KQ1, Q2, right? Um, uh, Charge on electron is negative, so minus E. What about charge on the sphere? Charge on the sphere would be Z E. Or I can also, they're asking what is the maximum number of photoelectrons emitted. If one electron goes out, charge on this will be +1. Two electrons goes out, charge on this be +2. Three electrons +3. So if n electrons go, it will be plus Ne. K Q1 Q2 by R value is given as 1 centimeter. R value is given. Now, when will maximum be emitted? Maximum be emitted if one time will happen when the incoming light will not be able to make any emission. Incoming light will not be able to make even one photon, one electron emission. So at that instant of time, this half mv square goes down to zero. If I say that sphere has got maximum charges, a sphere has got positive charge, right? It has got so much positive that light which is incident cannot overcome the potential energy. So the kinetic energy of emitted electron just drops to zero. Well, that is it. Once I equate this term to zero, phi is given as around 4.7 eV. Express this in terms of 12,400 by lambda in EVs. The only unknown in this equation would be n. Find the value of n. And once you find the value of n, you express it in the notation a into 10 power z, and you'll be getting the right answer. It is a combination of a lengthy question as well as a conceptually challenging question, two in one sort of a question. That is question number 22, right? So what did we do? We said that the light has to provide extra energy for the electron to escape, and that is in the form of potential energy. When will it be a maximum threshold kind of a thing? It gets so much positive that the kinetic energy drops down to zero. At that point of time, find the value of n. That is question number 22. Now, question number 23. The de Broglie wavelength of electron moving with this speed is equal to that of a photon. Okay. Find the ratio of kinetic energy of the photon to that of the electron. Here is where we need, uh, you know, conceptual help from de Broglie. Okay. 23rd one. The de Broglie wavelength is same. If de Broglie wavelength is same, if lambda of electron equal to lambda of photon, that would mean momentum of electron is equal to momentum of photon. Reason, lambda is determined only by momentum. Okay, fine. Then they are asking ratio of kinetic energy of the photon to kinetic energy of the electron. Energy of photon is always given by Pc, whereas energy of electron is given by P square by 2m. Remember relation between kinetic energy and momentum, P square by 2m, that's kinetic energy of electron, whereas energy of photon is P. Okay. With this information, they want us to find this ratio. How do I to go about it? Divide it. When you divide it, uh, uh, things would be getting cancelled. It would be Pc by P square into 2m. This P goes with the P in the denominator. It will become C by P into 2m. How do I know P value? P is nothing but mv. We know mass of electron. M into V, whatever V they have given, into 2m, right? Now, m's get cancelled. The ultimate answer you'd get is 2c by v. So, it would be 2 times speed of light by speed of electron, whatever they have given. You substitute, you'll get an integer as an answer. That is question number 23. Now, question number 24. The radius of an alpha particle moving in a circle in a constant magnetic field is half of the radius of an electron moving in circular path in the same field. Okay. Uh, what is the relation between de Broglie wavelengths of the individual uh, thing? Okay. So here is where we need to incorporate concepts from moving charges and magnetism also, which is R, the circular radius, R is equal to mv by qb or p by qb. This is a relation from moving charges and magnetism. Radius of a charge moving in a circular path, okay, it is P by QB. Going ahead. They have given the relation between the radius, same field, and they're asking relation between the de Broglie wavelength. So here it is. R of alpha particle is half of R of electron. So P momentum of alpha particle by charge on alpha particle is 2 times E times B should be equal to half of what is the radius of electron orbit? Momentum of electron by charge on electron, which is E into B. EB's cancel, the 2's cancel, and I get momentum of alpha particle is equal to momentum of electron. If momentum of alpha particle is equal to momentum of electron, then what can I say about lambda? Lambda depends only on momentum. So the lambdas also will be equal. So the lambda E is equal to lambda alpha. Therefore, the ratio should be 1. That is a preliminary calculation suggestion. Okay. R equal to mv by qd. R of alpha particle is half of R of electron orbit. With this, we can conclude. Now, question number 25. In question number 25, um, this is a nice concept. We know that light exerts a force on this surface, and that force is always upwards. And what is that force? This is a perfectly reflecting surface. It's a mirror, totally reflecting mirror. So for perfectly reflecting surface, the force component will always be 2p by c. Right? Now, the force exerted by light on this surface is 2p by c. So 2p by c has to balance its weight. Weight is mg. So 2p by c has to be equal to mg. So what is the power that is incident on the mirror? Power that is incident on the mirror is, look carefully, it is 30% of the power emitted by the source. So I can write 2 by C. What is the power incident on the mirror? It is 30% of power of the source equal to mg. That's it. They have given the mass 20 grams, G value we know, and we need speed of light that is also known, 3 into 10 power 8. And now I can easily get the power of the source from this relation. Interesting. Using light, you can actually levitate objects. A concept which can be, further taken up by even JEE Advanced. So these were the questions from dual nature of radiation and matter in your JEE test 3. So test 5. So hope this was helpful. Keep doing physics, have fun with physics, and revise the only question that needs to be revised again and again and again in this paper is only this question number 22, a very conceptual one, because the electron which is being emitted needs an extra energy from light because it has a bounded potential energy also. Okay, so that would be. This would be question number. This would be solution for question number 22. A nice one, revise. So with this, I would say I would wish you all the best for the next exam. Take care and keep doing this.